Hello, everyone. Please be seated. We're starting the last session of today in 2 minutes.
Okay, welcome to another session. It's now time for Alfred Arona to speak, and the title of the talk is "Lowering the Barriers to Working with Public Career uh, Level Data."
Yep. Um, Good morning. So my name is Alfred Auno. So today I will present our work on lowering the barrier to working with public area level data, and
Alfred,
this
if
is
you
done
could,
with my.
uh, Alfred, if you
Oh,
could
sorry.
maybe speak closer to your microphone or speak a little bit louder, that would be super
Okay.
helpful.
Sorry.
Thank
Yeah.
you.
Okay. So yeah, I was saying that I will be presenting our work on lowering the barrier for working with public area level data, and this has been done with a supervisor Ioana from Simla Metropolitan and Matthias from University of Twente. So the goal actually of this work is basically to of this paper is basically to introduce our consolidated data to the community so that you can avoid going through all the challenges while working with area level data. So next slide. Don't know how control. No. Next slide, please. Yeah. So the agenda of today, I will start with a little bit of background about the IR system. Then I will introduce the data, the original data that we have collected from the area, and talk a little bit about some inconsistencies that we have seen on the data. And I will finish my presentation with our proposal, our consolidated data. So, internet resources like such as ASN number or prefixes are managed by several organizations, such as the Regional Internet Registry on behalf of IANA and ICANN. So we have five internet registry, and uh, regional coverage, but they share basically the same core function. But for the purpose of this work, we decided to focus basically on two main functions. The first one is related to maintaining directory service, including whois, and each area actually extract part of the directory into publicly available whois and also delegation file, also called statistics file. Each area also provide reverse DNS for the delegation to the customer, and those files also provided they also provide the reverse DNS for this file. So we decided to use those data for a project. So we'll assume that this should be easy. So let's look at the data. So here we have two example actually of reverse DNS on the real level. So on the real level, we are expecting delegation to customers. So we are mostly expecting NS record. But you can see on the example, on the first example on the top, that uh, we also have IPv4 and IPv6, I would say, record that is not expected to see on the area level. The example on the bottom is classless delegation, which is the best way to delegate allocation lower than /24 using CNAME. And in this example, we have two adjacent prefixes, 169 to 1539 120/26 and 192/26, which are adjacent prefixes that had been delegated to two different name server. So why this data was important for us at the beginning of the project? Because we were looking basically to track, for example, limb delegation at the area level or map a prefix to a name server. So once we have the prefixes, we need to collect additional information about the prefix. This is where we go to the WHOIS dataset. So the WHOIS provide basically general information about the resource, and the way that the publicly available WHOIS data is presented, each WHOIS object is separated by an empty line. So here on the left, you have one example from Arin WHOIS database where they use the route attribute, which is not used by the other registry. The other registry use the init number attribute for IPv4 address. On the right hand side, you have two objects from LACNIC, and they use the init num, which is common across other registry, but you can see that they use custom notation for the init num object. So if you, for example, have your script running and you're expecting to see well from, for example, prefixes, you will encounter a lot of problem trying to address all those inconsistency on the init num, how the init num uh, attribute is used in this region. However, the WHOIS is still used by network researcher and operator. As I told you, as I showed, sorry, it's come with some limitations. So while we are working with this data, we decided to address some of the challenges related to this data. So in addition, we've seen that the data that is publicly available on the WHOIS is not, you cannot have access to historical data. So it's just one of data. Different area use different URL where they produce the publicly available WHOIS data set. And I show you there is inconsistency in terms of object and also key. So on the table, you can see what I just showed you on the previous slide. Aren is using the root attribute instead of init num for the IPv4 prefix, and there is no net name. Instead, Aren use description attribute. In Lightning region, there is no maintainer, there is no name, for example. So we try to fill those missing, I would say, attribute relying on other data sets. On the reverse DNS part, is similar to the WHOIS data. It's not possible to have access to historical data. We've seen an expected resource record, and in RFC 1035 is a zone file should at least have an SOA record in addition to NS record. But we've seen on the data that is published by the area that most of them do not provide the SOA record according to the specification. So we try to address those challenges with our consolidated data. So how do we proceed? We propose actually our consolidated data in a common format, which is interoperable and optimized. So we organize the data in a year, month, the hierarchy, so it's possible to have access in longitudinal. It's possible to have longitudinal analysis, and the data is also designed to support large-scale analysis tool. So we base our work on longest prefix matching, and we create what you call an identifier. So we have a start and end address that we use as a key for each record that we have from the WHOIS. We rely on the delegation file to complement missing information from the WHOIS. For the reverse zone, we also convert the domain to a prefix for both classless and classful delegation. We also apply the same idea of identifier. We have a start and end address that you use to easily identify each object. So, yeah. So here we have one example of both WHOIS and reverse DNS of the consolidated data. So we use some color code to show what we did. The black color basically show what was on the original data. The orange color shows the key that we introduced in the data. So we have the start address and the end address that we introduced on the data. The green shows the data that we that was missing. For example, in this case, we have the status and we have the country that we were able to uh, complement from the delegation file. And for the reverse DNS, we add a flag to show whether the data was from classless or classless delegation. So this kind of easier analysis when we want to compare classless versus classless delegation on the area level. Yeah. So to summarize a little bit, what we basically did is use the publicly available data from the WHOIS and reverse DNS data, and we try to address some of the challenges. So we add what you call identifier. So we have the start address and the end address that we can easier our analysis using these two limitation. We provide the data in a longitudinal manner. We start collecting the data since November last year, so the data is publicly available. The data is compatible with data engineering tool. On the website, we provide more information on the data dictionary, and we also propose a basic Python notebook that you can use to that you can customize actually for your own needs. So yeah, thanks for your attention. I think there is already one question. Thank you.
Tobias?
Tobias Siebig, Max Planck Institute for Informatics. I'm a little bit confused by the slide you had on the RIR formats, and maybe I just misunderstood something. But there it was said that APNIC, for example, doesn't have MNT objects, which I do actually see, for example, in the APNIC entry for quad 1. And I actually did a whois on the v4 prefix there, and that didn't have a route entry, but a net range and a CIDR range.
Okay, this you're talking about this table, right?
Correct.
Yeah. Okay. Yeah. So this information comes from the publicly available data. So we download the raw WHOIS the data set that are produced by each area, and we this is the baseline of the analysis. We use the publicly available data. So maybe when you run the WHOIS on your client, you are going to another, I don't know, which more enriched data from the registry. But this table is basically based on the publicly available, the one that is extracted and publicly available on the registry website. So yeah, maybe this is where the missing information comes from. Yeah.
Mark Hoster is Aaron. So I'm one of the regional registries here. So one of the things that, just to clarify, you're using IRR data to do your WHOIS work, as opposed to actually looking at WHOIS on port 43. So it's slightly different. I understand the confusion between the two. It is what it is. It's been years that this has been this way. So hopefully that helps clarify things like your question that you had here earlier. Thank you.
All right. Since we don't have any other questions, let's thank the speaker again.
One second.
So while we are trying to display your slides, we have Sapnil here that will be talking to us. Like, he will basically have a call for collaboration for DNS integration. And his slides are amazing. This is why we were just building interest here.
Clicker, yes. All right, hello. I'm Andrew Kaiser from VeriSign, and today I will be briefly detailing our lightning paper, a call for collaboration, DNS integrations. One of the ways the deployment of the global DNS has become more diversified is through the integration of DNS domain names into new application environments. Telnet, FTP, email services, and then, of course, later web browsing. In the past few years, we have also observed blockchain and decentralized applications have emerged as a new use case for DNS domain names, which can lead to new application integrations beyond the traditional use cases, such as email and web. One such use case is to use a user-friendly DNS domain name to be associated with a blockchain address or a piece of decentralized content, which can make it easier for users to interact with such applications. The way these interactions work is via a DNS integration. A DNS integration is a method that makes an association between a DNS domain name and a resource in an application environment. Today's integrations can be categorized into two broad types based on how the association is created, utilized, and maintained: DNS-based and server-based. A DNS-based integration primarily uses DNS records, while a server-based integration primarily manages the integration via a server. We will touch upon examples of both of these to show how they are used in both pre-existing and novel applications today. Finally, we will discuss some challenges that these integrations face, such as accounting for the domain name lifecycle, and why these challenges should be addressed. We will also suggest principles for a responsible integration between the global DNS and new application environments, in the hopes of starting a conversation now that can continue at a future IETF BOF and culminate in a set of best practices for different types of DNS integrations, so current and future applications will have a clearer path towards safely and securely integrating with the global DNS namespace. Now on this slide, we see a graphical example of some of these relations that I just mentioned. First, you register a DNS domain name in the global DNS, and then you relate it to an application. And one of the questions we always ask is, could this pattern repeat itself for new use cases? Now, before describing some of these use cases and the integrations they use, we want to highlight that many of the new applications are not just from the blockchain and decentralized application community. There are, in fact, many discussions happening throughout a much broader set of communities. The slide here shows a very partial list that includes IETF participants, IRTF participants, ICANN, W3C, CAB Forum, blockchain, and even private sector entities all engaged in discussions about DNS integrations. Now, given this wide range of integration from a number of organizations, and given that each integration makes their own trade-offs, it would be useful to bring these and other communities that we are aware of together at a future IETF BOF to start the process of establishing best practices around different types of DNS integration. To begin with, a DNS-based integration primarily makes this association between a DNS domain name and another resource using DNS records. This is the type of integration that most of us in the room are probably familiar with, because it includes the most common DNS use cases, such as using an A record to relate a DNS domain name to a web host, or using MX records for email services. These are the kind of integrations that you use on a daily basis whenever you open a web browser or use your mail client. Newer examples are coming from the decentralization application community, including through the use of W3C decentralized identifiers. For example, what Blue Sky is doing to link a DNS domain name to a W3C DID through a TXT record for their platform. Another example is the proposed W3C DID method, DID DNS, which stores a DID directly in the DNS as a URI record. If we dig a little deeper, There are also DNS-based integrations that can be used to initially prove control of a DNS domain name while the rest of the integration occurs somewhere else. And let's look at a couple examples to see what we mean by this. So the classic example is using your DNS domain zone to prove control of a domain name to be granted a web certificate, such as if you were to use the Acme protocol's DNS challenge. Now, once the user receives their certificate, they will install it on their web server, and the integration itself will take place outside of the DNS zone itself, because that certificate is installed on that server. A newer example of this comes from the blockchain namespace communities, such as the Ethereum name service and Tezos domains, which are using DNSSEC data and TXT records stored in DNS to prove that a given DNS domain name should be imported and integrated into their given namespaces. Now, DNS is of course used to prove this initial integration, but once an integration is made, subsequent interactions will occur in that namespace's ecosystem instead of in the DNS. And then the other type of integration that we mentioned in our Lightning paper is server-based integrations. And they make the association by managing content on a server. Now, compared to a DNS-based integration, you might wonder, how is this going to differ? And the primary reason it differs is that the knowledge of a server-based integration may not be gleaned from DNS zone data alone. For example, you may need to interact with an application that tells you that a given DNS domain name supports their application in some capacity, and you have to go to their server or some other endpoint to fetch data. Now, this can provide flexibility, especially in cases where storing such data in the DNS may not be feasible or desirable. A classic example of this use case is also the Acme protocol, which you might recall that we mentioned in the DNS-based integration. And in the Acme protocol, you can use an HTTP challenge to be granted a certificate that can then be installed on your web server. Now, this tells us something interesting about pre-existing integrations, in that they have methods to use both DNS-based and server-based approaches, such as the certificate being granted using either a DNS challenge or an HTTP challenge. And this kind of flexibility indicates that as we consider this topic moving forward, we will also need to consider multiple types of integration to support different types of applications. A newer example comes from the proposed DID web DID method, which stores a DID document on a well-known endpoint of a web server. And again, you'll notice a similar pattern here. There's a DNS-based approach for DID methods, DID DNS, that we also mentioned. So this flexibility appears to be important. I would also like to note that these are broad categories, and that not all integrations are going to fit neatly into a DNS-based or a server-based bin. What's important here for our conversation today is observing that there are many different approaches used by both pre-existing and newer applications today to integrate with DNS domain names. So it is likely that we will need to develop best practices for different flavors of integrations moving forward to ensure that different applications that target different use cases can choose an integration that best fits their operational profile and objectives. Now, with all these integrations in mind, we did want to discuss some concerns such as interoperability and support, but today I want to highlight the synchronization aspect of the concern. You can check our Lightning paper for a discussion of the other topics. Now, synchronization between a DNS domain name and other namespaces and applications are not guaranteed once the integration is performed. For example, the DNS domain name may be important, but there may be no clear process or mechanism or guidance to update the integration when the DNS domain name expires, is transferred, the zone changes, or the content on the server changes. Now, to ground why this is concerning, consider the following example scenario. First, a registrant will use a DNS domain name and a DNS integration to integrate that name into some application. Second, the DNS domain name will expire, but because the DNS integration is no longer synchronized, the now X registrant will be perceived as controlling the DNS domain name in this integrated application. Then, if the DNS domain name is re-registered, two separate parties will be perceived as controlling the same DNS domain name dependent on the application context. Users of the integrated application will see the information and data set by the previous registrant, while users of the traditional DNS applications will see data set by the new registrant. And of course, this will lead to confusion amongst users, amongst the DNS registrant themselves, and amongst the integrating application. So with that in mind, we would like to set forth certain criteria that we believe are important for any responsible integration method. The first circle on the slide is control. And this can be summarized as, can a DNS registrant be confident that only they or their authorized representatives are able to use their DNS domain name in the DNS integration in question without being concerned that someone else may be able to claim or use the DNS domain name without their consent or knowledge. The second circle is domain lifecycle. Does the DNS integration account for the DNS domain lifecycle to avoid such synchronization concerns as we just mentioned? Additionally, is an integration aligned with the best practices and policies of the DNS community? For example, if you support DNSSEC-based methods in your integration, do you support the required and recommended algorithms from the DNSSEC RFCs? And of course, does the integration expand utility without impacting the ability of the DNS domain name to be used for other purposes, including the pre-existing uses it was possibly being used for? So, with all of this background, we would like to extend an invitation for a collaborative community-level discussion that will be needed to address the issues in this space, to come up with responsible DNS integrations for diversifying the utility of DNS domain names into new application environments. So please feel free to reach out to us if you are interested in a future BOF on this topic, and please spread the word to other communities you are aware of. Thanks for your time today, and I look forward to interacting with many of you in the future.
Questions? Peter?
Hello, Peter Thomason. You gave an example about on slide 8, perhaps, of where the problem lies, and I think and the example you gave is essentially when I let my domain expire, I have a problem. Now, is that the main issue we're solving? Because it seems to me that that's maybe not best solved with integration concepts, but rather with not having the domain expire, right? So I wondered, like, what's the problem we're solving? Because that doesn't seem to be it.
Right. It depends on if you're looking at the synchronization issue from which perspective. Let's say, for example, that you might have let the domain name expire and you still continue to use the domain name in that integration because it just happens to work. So you don't realize there's been any problem or any issue. Or if we look at a blockchain example, if the name expires and you still are perceived as controlling that name in the blockchain namespace, and someone tries to send you cryptocurrency to that address, for example, but someone else now controls it in the DNS space, they may think they were sending it to the DNS party when they accidentally ended up sending it to whoever the previous party was. So that's part of the spirit there, is to try and solve both sides of maybe you let it expire accidentally, maybe you did it maliciously, but that way we can try and account for this or understand if it should be accounted for. Thanks for your question.
Jim Reed. Interesting ideas here, but I think the problem I've got is trying to figure out where this kind of discussion and collaboration could take place. You've given a whole shopping list of things that could be looked at for the future. Some look interesting, some maybe not so interesting. But there's a whole bunch of organizations and institutions that could be involved in this. We've got the IETF, we've got ICANN, we've got various other industry forum and so on going on. So where would you see this kind of collaboration and cooperation and discussions taking place? How would you think that could be achieved?
Yeah, an excellent question. Our first step really is to try and have a BOF to try and get more insight from the various communities involved to see who would be interested in tackling this question, because you're right that some of these topics seem to be better fits for the IETF, some seem to be better fits for more ICANN level discussions or W3C discussions, and it really sort of depends on who we can get into the room to discuss these topics and decide what direction at that BOF, for example, that we can take.
Okay, well, I've got 2 points to make first about that. Just to be a little bit picky here, if we're talking about a BOF, that's got a specific meaning in IETF context. And I think you probably don't want to have one of those kind of BOFs, because those BOFs are supposed to lead to a working group being formed. But certainly having some place where these people could come together for a group hug would be a good idea. I think one of the challenges you would have trying to make that happen is finding a forum or a venue for it. And I think some of these organizations are like to be very protective about, we're doing this little part of the problem space here, don't bother us with things that are going elsewhere. And I think that'll be a challenge to get these people to think they could come together and work in a collective manner to work at these problems.
Thank you. Yep, point well taken.
Hi, Daniel Kahn-Gilmore. So thanks for bringing this up here. I think you've outlined really a broad class of problems, and I think it can be challenging to get people to collaborate when, my use case might be something completely different from someone else's use case, and the only thing that we share is that we have some kind of integration with the DNS, right? I mean, I see this with encrypted client hello, fronting server DNS updates, for example. How do you imagine getting people who work across such widely different scopes to actively collaborate on this? And secondly, due to this, with the synchronization problem, one of the things that I think we see happening with the DNS is that the DNS is used as a leverage point to create things that then have a different actual time scale than the DNS records themselves. So like, if I use Acme to get a certificate, the validity window of that certificate is not bound to the validity period in the DNS. So how can we think about aligning those timescales, or is that hopeless? Like, how do you see that?
So to take that last question first, hopefully it's not hopeless. Part of the motivation here to try and broaden this collaboration is to bring sort of diverse communities together, especially ones such as the Acme community, who has a much longer history of operational understanding to help us influence and understand what maybe some of these new integrations might be able to do. And it might be the case that the scope is, I think as Jim was also alluding to, it might be too much for any one sort of venue. So it might be the case that we figure out as we interact and associate and have conversations and dialogues with people that we have to fine tune the conversation to target more narrow areas.
Okay, one place that you might want to look for inspiration is the UTA working group, the Using TLS in Applications working group. It's a little bit more focused than the possible places you can integrate DNS, but take a look at that and see how they've dealt with TLS in a range of different
Excellent,
spots.
thanks for the suggestion.
Next speaker is Johannes Nab, and he will be talking about, the title of his talk is Gotta Query 'em All Again. Repeatable name resolution with full dependency provenance.
Hi, I'm going to talk about name resolution, the stuff that DNS is all about, or maybe about. Let's start with an example to get us all back to speed. Yes. So, for example, if you're resolving tom.de, we start with the root hints, or we're going to talk about authoritative name servers. We'll start with the root hints. We have some name servers, names. We have some glue records where we're going to start. And for simplicity reason of this figure, because we're going to fill it in later, we're going to omit all the IP addresses. We simply assume that they are somewhere in the zone, meaning in the root dot. And for the authoritative server FQDNs, meaning the NS record names, we are shortening them and simply pointing to in whichever zone they are going to be answered, they are going to be authoritative in. So initially, we query the one of the root servers. We're going to get a delegation back for the DE domain and have the name servers. And in the delegation, we also, or the reversals, we also get the glue records that we then continue on. So on the next step, we can simply ask one of those servers where we get the glue record as well. For tom.de, we get an additional delegation back with 3 name servers. And for one of those name servers, because it's a sibling domain in the DE zone, we luckily also get a glue record back, and then we can simply ask this one and get our answer back. So during that resolution, we more or less relied on glue records. We have a heavy resolution path, but we found a lot of stuff in the DNS, all those zones in gray, where we don't know the name servers, we don't know how we get there or what they could influence. So if you're going to resolve them all, then we're going to end up with a figure that's going to be a bit more crowded and a bit more complicated. So how do we get to that figure? For every name that we get in a delegation, in a referral, we're going to resolve it, and we're going to continue until we have no more names to discover, no more names to resolve. And then we have multiple resolution passes on how we can get to our answer, and how we can, or also what can influence the answer. So what's the motivation? I mean, we want to find and resolve all recursive dependencies. We want to build the entire dependency tree that we can figure out what can influence the name resolution. We want to identify broken delegations. For some definition of lame, we called them previously lame. So like authoritative name servers that do not exist or do not seem to exist. So if I try to resolve a name, I might get an NX domain back in the DNS. It could be in the root zone if it's simply root crap. It could be in some TLD zone where I might be able to add my own records. Authoritative name servers that do not answer, timeouts, ICMP errors. It could be performance problems, and also performance problems, authoritative servers that don't answer or don't give any useful answers back, meaning various DNS error indications, non-authoritative answers, recursors that are entered into DNS errors. And in addition to simply getting the dependency tree, we also want to query them all, and we want to also query the multiple data, or query and compare the multiple data copies. What are multiple data copies, or what do we have in the DNS? We have NS records in the referral itself, but we also have NS records in the origin. Do they match? What can we learn additionally here? We have glue records, and we also have the glue records, hopefully authoritative data. And last but not least, we also have, for each domain, hopefully multiple authoritative servers. So are they all synchronized? Do they also have the same data, or do we have some configuration drift? Why is it important, or why do we want to investigate that? Number one is the security aspect. If there are some hidden dependencies there, some broken dependencies that could influence the resolution, and also the performance impact. If we have records or name servers that do not work, then we're going to maybe spend some time there, but not speed up the resolution for the user. Goals. For our goals. So our research questions are: we want to study the DNS dependency graph. We want to find potential inconsistencies and misconfigurations, try to evaluate their impact. But are left with a problem if we want to do that. Regular resolvers, common resolvers, do not expose that data. And they do not even internally necessarily get all that data, because they might rely on glue records. The primary task, the primary goal is get an answer to the user as soon as possible. That's more or less the benchmark there. So we did the only thing that we thought to do. We built our own resolver, foolishly in the attempt, because how hard could that even be? And for our implementation goals, more or less guided based on what we want to achieve, we want to discover all reasonable resolution passes. So if there's a hidden primary server, we are not going to brute force the entire IP space to find that server. We want to query all data copies as reasonable. We want to capture all those queries and save them, that we can later on provide provenance on why did we get that answer, why do we have an additional answer, why do we didn't get an answer. We want it to be deterministic, repeatable, and we also want it to be fair and efficient. So we don't want to overburden authoritative name servers, especially if we query all data copies. So we want to be a good net citizen. So implementation of such a resolver with a very rough overview here, because more details in the paper, because that gets a bit tricky on what we need to consider. So we structure the resolution more or less. We try to build our zone tree and how it's observable in the wild, how it's observable in the internet. We find all authoritative server candidates, meaning glue records, root hints. resolve the name server or the DNS names within the resolver, and also have to consider, like, if we have a name server that's authoritative for a parent and the child as well, we do not get a referral back, but we simply get, if we ask for a delegation or try to figure out the delegation, we simply get an authoritative answer back in the SOA record. And for all those candidates, we are querying the SOA record and the NS record. The NS record simply because that could lead to additional information that we can uncover. The SOA record should exist, might not exist for interesting configurations, might give some hints on whether or not they are properly synchronized, even if we don't see diverging data. And we consider the name server, and we are going to use the name server. Is any of those two queries is going to provide us an authoritative answer. If we get conflicting answers, then we're going to use the superset of them, because that's what if you want to figure out all resolution passes, that's what we need. And we end up with a problem like if we have names in the NS records that we're going to resolve within the resolver, we're going to add new zones, we're going to discover new stuff in the name, or they are also going to have name records. So is it resolution all the way down? Let's get back to our figure. If we squint hard enough, I mean, it's already oriented that way, we're going to find some zones that seem to interdepend on each other. Like, for example, lrz.eu, lrz.de, lrz.bayern are all zones that point to each other, where the name server records point to interlink or interdependent to each other zone, including itself. If we go a bit back to graph theory, we are going to find out, or that looks a lot like a strongly connected component. Meaning, from each node, I can in this group, I can walk each other node and come back to the origin, and I can influence myself. For the DNS impact, that means that if I have a name server in such a group that's going to provide an answer, if it adds additional information, it might be even able to impact its own zone. If we fill that in for everything, we are going to end up with our more or less structured dependency tree, and have also the additional completed graph. We're going to complete the resolution process, or it's based on postponing our queries until we figured out these strongly connected components by an online graph search. And we are going to need to, that's details in the paper, a bit dense on how do we figure out what are the name servers. We get queries. Do I need to resolve that query in order to complete the strongly connected component? Or if it's not needed, then I can postpone it. So in order to figure out those strongly connected component, we need our zones. We need to detect on what might be a zone, what can be externally observed as a zone. So we need to, for all dots within the zone, we need to figure out, is that a zone? Is there a delegation there? Or is that simply a subdomain in another zone? So QNAME minimization provides a framework for that. So we simply query for each delegation. We're going to query, is there something that's a delegation for the specific name and not only the complete name? And compared to the receives or the suggestions, we're going to use SOA queries. Since for A queries, we have the problem example that if the parent is also authoritative for the child, we're not going to discover this delegation, even if it exists. For NS queries, that's what the original proposal was. I tried that once, and I found some interesting name servers that answered in delegations in the answer sections. I don't want to know. And as an additional optimization, because even the last label could be in a separate zone, if you have ... it's most likely not going to be in a separate zone. So initially, for all those labels within our single labels within the second level, effective second level domain, we're going to ignore that for now, and only going to do a full zone cut discovery in NS records or records if we get an answer back that indicates a delegation. So if we query all name servers, that might be not completely viable. For example, the root for the .com zone has 26 authoritative servers based on IP addresses. There might be more servers, there might be less servers. I'm interested on information there. And it's a very large zone. So if we resolve a lot of names, we're going to hit a lot of very signed name servers. And if we employ rate limits on our own, that's going to be the bottleneck for our resolution. And I would assume that VeriSign as an operator would probably prefer to not answer the same questions 26 times if we can avoid it. What's the solution here? We can simply, we extend or assume that TLD servers are somewhat synchronized, consistent, properly managed, and simply query a deterministic subset of the name servers, so that we don't have to query 26, but pick 3 based on the name that we are currently asking, based on the IP addresses of the candidates that we can ask. And if we find any discrepancy, so if our assumption they're consistent, we observe that it does not match, we're going to query all. Additional optimizations are if we have zone files, for example, from the centralized zone data service, we can use those delegations that we find in those zones directly and skip querying the .com name servers completely. For testing, I mean, if you implement a resolver, that's going to be a lot of bugs, trial and errors, and a lot of gray hair. Rerunning against the internet is not a viable option because it, number one, burdens the authoritative servers. We don't want to be a bad net citizen. And even if we would do it, the results are not one-to-one comparable. If there are changes in the DNS, we don't know if it's code changes, if it's bugs in our code, or if it's simply DNS changes. So we have a procedure on where we capture the previous recorded data and run it, simulate the name servers that we've seen in a Linux network namespace, and can then record queries that we've, unknown queries, meaning queries that we've not in the original data, but queried now after in the simulation. And we have also queries that we know in the original data, but we skipped in the simulation right now, so indicating bugs. Due to timeout handling, unresponsive name servers, that's comparing the results. If you run it multiple times, if you run it against yourselves, is a bit more complicated with more details in the paper. So let's conclude. We have a resolver that can discover the entire dependency tree, provides a repeatable and deterministic resolution process, independent of caching, ordering, etc. We're saving all reasonable resolution passes, including all authoritative servers that we can ask for later analysis, and have a process to test that. We have a sample data set on tcpresolve.github.io with an outdated Alexa list, which no longer are up to date, and a majestic million list for a reasonable record set, including www subdomains, and a few name servers, a few domains that might be interesting. That's only a sample data set. If we have, there exists more data, but that needs to be analyzed. Those impacts and misconfigurations need to be evaluated. And I'm especially here interested in, are there new interesting questions that could be answered by such data sets? Do you have information, or do you have input on what needs to be considered additionally, and open for questions?
Daniel Kahn-Gilmore, thank you for this work. It's a giant disaster. I'm impressed that you've persisted at it. Were you doing so I'm trying to understand the relationship between this and QNAME minimization, because one of the problems that we found with QNAME minimization, if I remember correctly, is that you could get different answers if you were sending the full query as opposed to the suffix to the higher level name servers.
Yes, I mean, if there exists the possibility that the parent name server is a hidden primary for a child.
Right.
That simply could be an old configuration that's still on the server, but it's now delegated.
Right. Or a malicious response.
Malicious, and it's especially if there are multiple levels, like a sub child of a child, because then if I ask for the child directly, I get a delegation. But if I ask for the child name, grandchild name, the answer the server still has the zone configured and is going to answer directly.
Right.
So there are some differences that could happen there. Not sure if that's the question exactly.
So I guess my question is, were you able to analyze this to identify scenarios like that where that happened? Because I mean, one of the concerns that I have is that these things are possible and we wouldn't notice them today.
Yes, I did not analyze that specifically. I hope the data at least could give some indication where that could happen. And since we know all the name servers that we could ask to verify if that's the case or not, I hope that would be possible to figure out.
Okay. The other thing that I think would be very useful, and I don't know if you've produced this or not, would be something that a domain administrator, someone responsible for a given DNS record, could run that would do all of these queries and map everything and give you the kind of diagram that you gave to show, here's the range of answers that I got and here's the path that I got to those answers from. Do you have such a thing?
No, unfortunately not yet.
Okay, that would be really nice to have.
Yes,
thank you for doing
I agree.
We will take one more question, and that would be from Victor.
Me, Victor?
Yes.
Okay.
Find me later.
Okay, I think I'm unmuted. I was going to ask broadly, what uses have you put it to? It looks like you're making the data sort of available for others to poke at a little bit. But what have you done with it?
What we've already done with the data, if I understand the question correctly, yes, no.
What are the applications so far?
So the applications so far, more or less the engineering challenge. I looked a bit into the data. There are a few scary things, like if you find NX domains for name server records that point into top-level domains, where I did not yet figure out if they are completely registerable or not. That's the scary part. And other than that, there is data, but I did not completely evaluate it yet. Initially, it was the engineering challenge that was the interesting part.
Great. Let's thank Johannes again. Next, we will hear about enabling multi-hop ISP hypergiant collaboration from Christian Monteno.
Hello, am I audible?
Yes.
All right, good. Hello, everyone. My name is Christian, and I would like to present today my work on enabling multi-hop ISP hypergiant collaboration. So let's start. Looking at the internet nowadays, we see that more than 80% of all the traffic is coming from hypergiants, namely Google, Netflix, Meta, and more others of them. Now, who they are sending this traffic? Well, usually those are the ISPs like we see here, AT&T, Airtel, Earthlink. In order to do so, the hypergiants tend to interconnect as much as possible. So they tend to connect to as many networks as they see fit. Now, nowadays, large hypergiants appear more than 10,000 different networks. And for example, we see here like Cloudflare already reached the 10,000 and Google has more than 12,000 networks. However, just connecting to the ISPs is not enough. So in order the second thing that hypergiant has to do once the client wants to access some resource, the hypergiant needs to select the optimal server, right? And this problem is not trivial because there are a lot of things that are changing on the internet all the time. However, previous work by Puyol et al. Designed a system that actually helps the hypergiant to select the best server, but just for those ISPs that are directly connected to the hypergiants, right? And here comes the question, how about the networks that do not actually peer with these hypergiants, since the largest one goes up to 15,000 networks, it means that there are more than 40,000 small network guys out there that really don't appear to a hypergiant. So during our collaboration with a large European transit provider, we actually saw that a really large number of these small ISPs do not peer with the majority of the hypergiants, and they actually rely on their transit provider. Let's have a quick look. We have here on the left side an actual hypergiant that would like to send some traffic to a small European ISP. And the first thing that it does, it will send the traffic to the transit AS. As we can see, the traffic is split in two different locations. In this case, it's two different countries. And what the transit AS will do is it will just simply pass over, if it can, all this traffic to the small European ISP, right? So in this case, it will just move forward to some other routers, but will keep to the same location. Now, what will happen in the small European ISP is that some of the traffic actually needs to be rerouted from one location to another in order to reach the end clients, right? And in this situation, we have this small different amount of percentage that actually went to one location but needed to be in another location. Further investigation, we made further investigation here. We looked at all the router and their capacity. There are no congestions. There are actually no problem anywhere. The only issue that this is happening is actually the improper choosing of the server on the hypergiant, right? And now if we try to look at the entire week, we want to see what's happening over the entire week with the traffic coming from the hypergiant. And what we see from the total traffic coming from this hypergiant, we see a typical diurnal pattern. It's very typical for a residential ISP with high peaks in the evening. And when we look at the non-optimized traffic, we see that it kind of follows the same pattern. But what's most important for us is that there is a large amount, so the non-optimized traffic is very high during the peak times, right? So it's almost 30% here. Now, we see this behavior in more than 20 European ISPs during our collaboration with the large transit provider. And we asked ourselves, is there the possibility to help the hypergiants to improve the server selection for non-directly connected ISPs, right? So can we actually reduce this 18% or maybe completely remove it if it's possible? And in fact, the answer is yes, we can do that. And we can do that by enabling the ISP to hypergiant collaboration. The idea is that the ISP needs to send some additional information to the hypergiant in order to improve the server selection. This sort of collaboration can go multiple ways. For example, you can have a multi-hop collaboration where the ISP collaborates directly to the hypergiant and no other in-between transit IS. If there are multiple, if only one of them is involved. Another sort of collaboration can be 1+ hop collaboration, where there is a chain of collaboration between all the neighbors, starting from the ISP, ending up in the hypergiant. Multiple other collaboration are possible, and we discussed them in our paper. So if you're interested, please go ahead and read. But for our presentation, we'll focus on the multi-hop collaboration. The idea here is that the ISP would like to send a set of key value pairs to the hypergiant, where the key is an IP prefix of the ISP, and the value is a list of these similar IP prefixes. Give you an example, you can interpret it as a letter in sort of, dear hypergiant, can you please send data to prefix A as you do for prefix B or for prefix C in this order of preferences, right? Now, once this is set, the idea, the question comes up is, how does the ISP select these prefixes? What prefixes should it choose? And we reduced it to 3 different possibilities. You can go either with BGP announced prefixes, which is actually not efficient since the hypergiant already knows them and takes them into account. The second one is the ISP DNS resolver working prefixes. And the idea here is that inside the ISP actually uses a small fine-graded prefixes that it's working with, especially for the DNS resolvers of the clients. And we call this in our future in the future slides. We'll call this specific work prefix is the DNS default. A third option is complete disaggregation, like /22 disaggregation, where we can disaggregate all the prefixes of the ISP up to /24. The thing here is that both the DNS resolver and the DNS server should have the ECS enabled. Now, going back to our traffic and the unoptimized part, we ran a retrospective simulation on this real traffic. And as we can see with the DNS default simulation, we managed to reduce from an average of 18% down to 1.3% of the amount of non-optimized traffic. Now, if we use the /24 prefixes, then we end up with fully optimal traffic in here. This was the case of only one hypergiant, and we went forward and we looked at all the traffic that's coming to that ISP. And we identified 11 different hypergiants there and also some other networks that are sending traffic. As you can see, 3 of them here are marked with a star. The point is that for these 3 hypergiants, they only connect in one location with the transit AS. Therefore, it doesn't really matter whatever server they will choose. There is only one possible way to send the data to the ISP. So the further optimization can be done only by the transit AS itself if it wishes to do something, some changes inside of it, internal routing. The next column shows you the amount of traffic coming from these hypergiants, and also the following up the amount of non-optimized traffic that is there. As you can see, overall, there's about 14% of the traffic that incoming coming to the ISP, and this 14% have the potential to be improved. On the last column that we have here, we see the amount of non-optimized traffic per own traffic share, and we see a large discrepancies in between hypergiants. So for example, for one hypergiant, the traffic is actually pretty well optimized and the server are very well selected, and there's only 1.8% of non-optimized traffic, while for the other hypergiants, we see almost a half, 46% in this case. So looking over the time, on all the traffic that incoming into the ISP, we see the average of 14%, and we see again the same diurnal pattern of the non-optimized traffic. Once we ran retrospectively our simulation with the DNS default, we managed to reduce the amount of unoptimized traffic down to 4%. What's more important is during peak times where the resources are really scarce for small ISPs, we managed to reduce it even more. So in this case, as you can see, from 30% down to 10%. If we ran the simulation with the /24, we again ended up with optimal traffic. Right. Going to the conclusion, during our research, we showed that it's possible to improve server selection even if there is no direct connection in between the hypergiant and the ISPs. We also showed, using real ISP data, that our system can actually improve the non-optimized traffic up to 10% without any additional implementation or improvement to the DNS. I'm trying to say about implementing and adding ECS to the DNS. Also, our results show that there is a discrepancies in between the traffic coming from different hypergiants, and for some of them, there's up to 46% of the traffic that's coming the non-optimal interconnection. And we argue that out there are more than 40,000 different networks that can potentially benefit of this system. Thank you.
I can ask something since nobody's waiting, right? Okay. Thanks for the presentation. Can you comment a little bit more on how likely is it that a hypergiant will have alternative paths that BGP can expose? Or like, how do you really change the path that is being used?
Well, actually, we we don't want to change any paths at all, right? So the idea that what BGP did and how the paths are selected is all fine. Our point is that unfortunately the hypergiant has not enough information when the request comes in order to select the proper server. And by accident, some distant server coming from a different place may be selected for that client, and then a different route will be used. So it will be the best route in between the server and the client, but it's just the wrong server, or not the best server was chosen.
And the servers that you are allowed to use, can you comment a little bit on the set of those servers? Like which servers are they on the same AS, or like what do they have in common?
So no, they are not in the same AS. So during our collaboration with this transit AS, we know for sure that there's no presence of the hypergiant inside of the transit AS. So therefore, once the hypergiant wants to send traffic from its servers, it's from inside the actual hypergiant. It has to send it via the transit AS and end up in the ISP, right? So
yeah, my question is more the servers that you actually selecting among, right? So if you're saying that the hypergiant does not select the optimal server, correct?
yes.
So what do this set of servers that could be selected have in common?
Oh, but they basically similar. They are duplicates, but they are in different locations. And the idea is that which of them will respond to your client, right?
Gotcha. Okay, thank you. All right, since we don't have more questions, let's move to the next and last talk for the day. It's from Alex Huang Feng, and the talk is entitled DAISY Practical Anomaly Detection in Large BGP MPLS BGP SVX VPN Networks.
Yeah. So hello to everyone. I am Alex, a PhD student at INSA Lyon, and we are presenting today DAISY, our framework to detect anomalies in large-scale BGP MPLS and BGP SRv6 VPN networks. So I will first present the scope of our project. What do we consider an anomaly in our BGP MPLS and BGP SRv6 VPN networks? I will go through the different DAISY architectures we've been working on, the IETF contributions we've working to have not only an open source solution, but also a standard IETF solution, and at the end, the first results and the ongoing works of this project. So a VPN allows having a connectivity for the customer between two or more sites. And in this project, we define an anomaly as an event that occurs in the network and impacts the customer traffic, and therefore makes the customer unhappy. This event can be provider inflicted due to an incident inside our network, a fiber cut, an interface not working properly. It can be also provider self-inflicted when there is a maintenance window and the operator is pushing a new upgrade, and in this upgrade there is a bug. But it can also be customer inflicted when the router, the customer edge router, but that are managed by the customer themselves, they push a wrong configuration to the router and they lead their own traffic to a black hole. So why this is important for ISPs? But because at the end, if you manage your outages badly and they last, you end up in the news. We all know that issues happens to all the network, but what it matters for ISP is how you manage them. This service interruption, of course, they make you look bad, but cost you a lot of money. And that is why we, in this project, we are focused on how to detect these anomalies at early stages and how to provide the necessary information for network operators to analyze the data, find the root cause, and of course, fix the issue at the end. So this is a project that is financed by Swisscom, and we do research, but also development in open source throughout all the chain. So from getting the data from the network to get visibility of what is happening in the network, we do research, but also standardize the telemetry protocol at the IETF and implement different publishers and collectors to get this information. We propose also new network measurements that could be interesting for anomaly detection. And at the end, the final goal of this project is having a scalable solution of course, anomaly detection. So first requirement of the project is that it needs to work. We are working with Swisscom in production data, and we need to take into account the different operational constraints that network operators they have. Let's present the different components we've been working on in DAISY. So first, we will understand that we need to know the behavior of the customers to make it work. I will go through the different standards we are using to get the different dimensions we are getting from the network. How do we post-process them? And at the end, based on that data, how do we detect anomalies? And of course, once we have detected the anomaly, how do we report them to the NOC so that they can fix the issue? This research, as I said, is based on production data from the Swisscom VPN network, and we quickly realized that customers differ a lot in their behavior, and therefore there is no one-fits-all algorithm to detect anomalies. For example, there are customers that are super predictable with flat curves of traffic or repeated day-night cycles, but there are also some other customers that, for example, regular drops of packets is for them normal, and therefore we cannot use these drop metrics to detect anomalies for them. On the other hand, they are managing around 10 to 11,000 VPN customers. We cannot do one recipe for a customer, and therefore we need to group the customers into customer profiles so that we can base our anomaly detection recipes on this profile. So we are getting different dimensions from the network. So first, for data plane, we are using the IPFix to get traffic counters and packet drops from the network. In control plane, to get the BGP topology and the BGP state, we are using BMP, capturing BGP events such as updates, withdraw, and peer downs. And in management plane, it's still a bit a work in progress at the IETF, but we are already deployed YAML using UDP Notif to get the interface state changes. And of course, YAML is to get all device-related information. Of course, once we have got all this information by the collector, we need to correlate this information to the customer so that we know to which customer we are impacting. And we are correlating IPFix to the BGP path so that we know which counters belongs to which customers. And we are doing the same for the interfaces of YAML to know when there is an interface which goes down to which customers we are impacting. We are doing all this with the open source solution PMCCT developed by Paolo Lucente, and this allows us to rely not in the inventories, but in what is happening in the network. So once we've got the data correlated to the customer identifier, we base our our anomaly detection on the customer profile. For each customer profile, we apply a set of strategies that are a way to capture the service health. These strategies are organized by a set of pipelines that are a sequence of conditionally checks, and the checks are the actual algorithms on the data that detect if there is something wrong on that data. A simple check, for example, would be check if for that customer at that time, if the traffic is, there is a big difference from the last week. If there is a big difference, we raise the alarm. Of course, all of this is configurable. We also allow plugins so that the network operators can define their own rules and integrate them easily. And of course, once we've detected an anomaly, we need to report them to the network operator so that they can fix the issue. For that, we are interfacing with Swisscom through a Kafka topic so that we are sending a ticket to the NOC and so that they can get the data. Within this message, we are giving them also the raw data from where we have executed the algorithms, but also the details and the parameters of the different checks we have executed so that they can have the full view of what did we raise this alarm. Since we are in a big data, we cannot save all the data. When there is an incident, we are saving this data in a permanent storage to play around with what if scenarios, to experiment with new strategies and new checks so that we can continue improving anomaly detection and continue improving the accuracy of our platform. As I said at the beginning, we are also contributing a lot within the IETF to not only have an open source solution, but also a standard solution with the different RFCs. For example, we have proposed a UDP-based transport for YARN push to allow the streaming of large amount of data from the router directly from the light card without stressing the route processor. Of course, at the IETF, we have seen that there are new technologies, segment routing over IPv6, that are starting to be deployed. We are proposing also extensions to IPv6 so that we can monitor these new technologies through the same system. And we are also proposing new metrics. In our case, is the on-path delay, which is the delay between the encapsulating node and the different nodes along the path. And we are exporting these delays using also IPv6 so that we can already have the aggregation from the node. We have also other contributions. I will not go into details on each of them, but please, if you are interested, please ping us. But basically what we are doing is extending the YARN push header so that we can actually monitor not only the data, but also monitor the whole pipeline of YARN push. And in the second instance, we are also extending IUM direct export so that we can compute in passport mode the on-path delay that we proposed earlier. So what's the status right now of this project? Right now, this project has been developed in Python as a proof of concept, has been deployed in production for a subset of customers of the Swisscom VPN network. And so far, we have detected 6 outages, 3 in real time and 3 in replay mode. And currently, we are continuing studying if there could be new dimensions that could be interesting to detect these anomalies. And of course, at each IETF, discussing with the different vendors if our different drafts could be actually be implementable. In the future, we also plan to study if the same framework could be also be used to detect anomalies in internet policies, since at the end in ISPs, it's another service, but they use the same system in a way of monitoring. So in a way, in our system, they could be another profile with different recipes dedicated to internet services. And of course, at each IETF, we are present at each hackathon, but also different working groups to continue progressing with the standardization. So that's it for me. If you have any questions or you are interested actually in any network telemetry topic, we are a bigger group than the authors of this paper. Please ping us, reach out. We are currently at the whole week at the IETF, and at each IETF we are present, working with Swisscom, but also different vendors such as Cisco and Huawei.
If there are no questions from the audience, I can chime in. So from all the data that you have seen so far and like all the different incidents, can you comment on the more common or the more disrupting one? What would you, like what's the worst, the more common one?
From the different incidents we have seen, there is no common incident because it was common. We would just have fixed the issue and not see it newly, right? So no, from all the incidents we have seen so far, each incident is a new one, and we've learning new things from that incident and implementing so new checks, new strategies to see if we can improve it.
Sure. I meant more like what was the more influential telemetry metric that you have done that catches many anomalies, for example?
Okay. So yeah, most of them, they impact a lot on the traffic amount, so on the forwarding plane. But when there is something happening on BGP, for example, you have a lot of spikes on the BGP events. So mainly on right now, at least on control plane and forwarding planes.
Thank you. Okay, let's take next speaker again.
Okay, so it looks like we're ending the workshop right on time, and I would like to thank everyone for joining us today and for asking those interesting questions. Please always feel free to reach out to the speakers if we had to cut your questions due to time constraint. And I would like to also thank our speakers once again for those insightful research talks. Do you have anything to add?
Yeah, I want to also add to thank our panelists that were super insightful and every one of you for the really nice questions and participation.
Yes, and it's our pleasure to be part of ANRW. And we hope it will continue to bring new ideas to the new community and to this community, and will continue to be more dynamic and lively. Okay, so let's call it a day, and thanks everyone for coming.
And thank you, Maria and Francis, for putting this together.
No, there was some more. Just say stop working.